now we are going to observe another important equations. So two more important equations. They are very much useful for solving the boundary value problems. They are called as Poisson's and Laplace equations. They are very easy equations, but the solution may be a little bit confusing or different. But the equations are so very easy in their basic form. So what are those equations? Just we will derive them using our Gauss law. Already we know the Gauss law gives us a relation that del dot D is equals to rho v. So this del dot D is equals to rho v will be modified now. Instead of this D, what I am writing is del dot epsilon E is equals to rho v. For a dielectric medium, just D can be replaced with epsilon E. And we have a relation between this E and potential. That how they are related? That E is equals to minus gradient of V. So the electric field intensity can be obtained from the potential using this gradient equation. So this E can be replaced with that gradient of V minus gradient of V, which is equals to rho v. Simply this equation is said to be the Poisson's equation for non-homogeneous medium. This condition is very important that we need to remember. This equation is said to be the Poisson's equation for non-homogeneous medium. Since it is non-homogeneous medium, I am not taking this epsilon to the out. So from this del operator. If it is homogeneous medium, we can bring it out this epsilon from the del operator. So clearly write down this one as a non-homogeneous medium. And this equation is our Poisson's equation. For homogeneous medium, how this equation can be written? Del dot, and this epsilon can be taken out, del dot minus gradient of V, which is equals to rho v, that what we have here. And if you modify this one, del dot del is del square, right? So this is del square V is equals to that, rewriting this one we'll use as minus rho v by epsilon. This equation is said to be the Poisson's equation for homogeneous medium. So just observe here, from the basic Gauss law, what we did is just we modified these terms. D can be replaced with epsilon E can be replaced with minus gradient of V. So del dot epsilon minus gradient of V is equals to rho v is the non-homogeneous medium Poisson's equation. And for homogeneous medium, this epsilon can be brought out, that is minus rho v by epsilon. These two are the Poisson's equation for different mediums. A special case of these two equations is called as Laplace equations. What is that special case? Simply the region what we are considering is charge free region. That this rho v will not be there. Since we are considering a charge free region, rho v is equals to 0. So if you substitute rho v is equals to 0, this equation now becomes del dot epsilon minus gradient of V is equals to 0. Simply this equation is said to be the Laplace equation for non-homogeneous medium. And if you take this one, then it is del square V is equals to 0. Since it is charge free region, rho v is equals to 0. Del square V is equals to 0 corresponds to a Laplace equation for homogeneous medium. So what we have to do is just you need to remember these two equations initially. Just remember this equation, and from that equation by substituting different conditions, homogeneous medium, charge free medium, we can observe these four equations. They are our Laplace equations and Poisson's equations. They will be very much useful for solving boundary value problems. So if you know what is the solution for this one, and the boundary conditions must be very much known to us.